Okay, now to find the value of this differential solid angle, we'd want to calculate the area of this little portion of a sphere that of the surface of a sphere that I've indicated with this red hatch marks, and divide that by r squared, just according to this definition here, a over r squared. Okay, so the way that we can do this is first we can calculate the circumference of a circle, which is the circle that is defined by this angle theta. Okay, so the distance between the observation point and the edge of the circle is r. Okay, and the radius of this circle is actually r sine theta. Okay, because it's with respect to this axis here, and so the circumference of that circle is 2 pi r sine theta, and then the arc length of, so it's almost like a cylinder except for it's not exactly cylindrical, but if we multiply, if this d theta is small enough, we can almost treat it as we can essentially treat it as a cylinder. So we have the circumference of a circle, and if we multiply then by a depth, if it was a true cylinder, or a height, then we would get an area. Here we want to multiply it by the arc length, which is just r times d theta. That's the arc length of this little portion here. So if we multiply the circumference by that arc length, then we get something in units of area. And again, if d theta is small enough, then this becomes identically true. Okay, and so we divide that then by r squared, and that's our differential solid angle. When you do the math, it's just 2 pi sine theta d theta. And we'll use that later. Okay. Now let's get back to the scattering problem. That is, we're shining a beam of particles. Rutherford was shining a beam of alpha particles onto a thin gold foil, a thin gold target. Okay, and so let's consider. So we have to talk about a beam of particles, and let's imagine that the beam of particles has all the particles in the beam have the same energy, and they're all going in the same direction. So it's as if you're just have some sort of gun that you're shooting out these particles, and they all have the same kinetic energy. They're all the same kind of particles, same kinetic energy, going in the exact same direction. This is approximated reasonably in the Rutherford experiment, because remember, he used this lead box with just a small hole in it, so that the alpha particles could only come out at very small differences in angle. So they're essentially all going out in the same direction. So we can define the beam intensity as the number of particles per unit area per unit time. Okay, so I, the beam intensity, has units of 1 over meter squared times 1 over seconds. Okay, so it's the number of particles per unit area per unit time. If we imagine that the beam has a cross-sectional area A, okay, so now I'm drawing down here a beam with some cross-sectional area, and again, they're all going in the same direction. All the particles in the beam going in the same direction, so we can define it sort of a cylindrical, if you like, whatever shape, but in this case I've drawn it as a cylindrical kind of beam, and it has a cross-sectional area A. Okay, and that's essentially that cross-sectional area is intersecting the target. Okay, and the target has some thickness x and a density. The density of scattering centers, the density of atoms, let's say, in the target is rho. We'll call that rho, and that has units of number of mass per unit volume. Okay, and again, the target has a thickness x. Okay, so the number of target atoms per unit volume, okay, in the target is just equal to, which we will designate as little n, is equal to the density of the target, that's the mass density, times Avogadro's number, that's the number of particles in 1 mole of substance, so that's 6.02 times 10 to the 23rd, divided by the molar mass, m, big M, which is just the mass per unit volume.